In the last videos related to the lecture series of turbulence modeling, we derived Reynolds equations by time averaging Navier-Stokes equations. Because of the averaging, we introduce these extra terms in compared to the Navier-Stokes equation. These extra terms are defined as Reynolds stresses, and we also attempted to close this equation by modeling these Reynolds stresses termed as turbulence modeling. And one of the modeling one of the technique we applied is using the same Newton's law of viscosity. We try to model the stresses using the rate of deformation strain relating to the rate of deformations using the viscosity. Here the viscosity is termed as kinematic turbulent viscosity. And the way we try to model this turbulence can be like two models, like algebraic model and also two equation model like k epsilon model. So this k epsilon models try to make additional two equations for, and we can have this turbulent viscosity to have a relations from formulating using the turbulent kinetic energy and the dissipations. So it has a few advantages and as well as having a disadvantages. Advantage is very simplistic model. It has wide, well established theory, and it has some excellent performance in many industrial environments, but there are some poor performance in unconfined flows and non-circular ducts. So in this video, we see that we, instead of making an analogy of Reynolds stresses relating to the rate of mean deformations and introducing the turbulent viscosity, we try to model the Reynolds stress directly and try to find out Reynolds stress equations for each Reynolds stresses. So 6 Reynolds stress equations we formulated in addition to that Reynolds equations. So those formulate that the Reynolds transport equations have this terminology, like the rate of change will be related to the convection and the diffusion and also production and dissipation. In addition to that, there is another two terms which contribute to the rate of change of the Reynolds stresses. One is from the pressure strain relationship, another is due to the transport due to rotation of the Reynolds stress terms. So here the production term is as similar to as in the previous epsilon k epsilon equations. It is related to the strain changes in the flow variables, momentum variables, and the diffusion term, as usual, like in other convective diffusion equations, is related to the divergent gradient term, and dissipation term is related to the dissipation terms occur in the k epsilon model. The present strain term is an like a peculiar term which is appeared in this stress equations, is because of the pressure fluctuation, because the ADs are interacting with each other, and also there is some difference in the mean velocities. Because of that, the pressure variations occur. Then that interactions with the between the ADs causing this additional appearance of that. So this pressure strain relations can be modeled using this expression 3.49, and rotational terms can be modified using this 3.50. So using this relation, we can try to model for each Reynolds stresses. In addition to that, an epsilon term occurring in the dissipation terms can be modeled as similar to the k epsilon model for a separate equation like 3.51. So the terms are similar, like convection, diffusion, production, and the destructions. The boundary condition is similar, like kind of an k epsilon model. We have a distributions of Reynolds stresses and epsilon values in the inlet, and outlet is a Newman boundary condition. And this is free stream is 0, and wall function similar to that k epsilon model, like a high Reynolds number we have using the law behavior, universal wall law behavior, and try to model the Reynolds stress equations, Reynolds stress terms. And for low Reynolds number, viscous effect has to be taken into account, so that we try to modify the Reynolds stress equation similar to that occurring in the k epsilon model, including the viscous effects into the diffusion terms. So these are the things, and though it's really seems to be a complex, but it's a simplest model which could potentially can directly capture all the Reynolds stress directly into account, and so that description of mean flow properties are really captured well, not try to identify some empirical values for case by case adjustment. So, but one of the disadvantages, it's not that well validated as similar to the K epsilon model, and also of computationally high cost. So these are the advantages and disadvantages. It's very accurate, and all analyses are modeled directly. But however, addition of K epsilon equations, still they have some limitations in applying to the unconfined recirculating flows. Hopefully we'll come up with the further turbulence modeling lecture, possibly describing the algebraic variations of the Reynolds stress equation in the next video. Thank you.